Good day to everyone. This is Aruna and welcome to my channel. Today we will dive into an exciting topic, alpha beta pruning, that combines technology and creativity. We will explore how AI enables non-player characters, that is called as NPCs, to exhibit intelligent behaviors, and how adversarial games create competitive environments and various programming approaches used to enhance game AI. The agenda of this video presentation is: first, we will look into AI in games and adversarial games. Next, we will explore the approaches to solve these adversarial games. In that, we will discuss deepening the evaluation through MiniMax algorithm and alpha beta pruning algorithms. First of all, we need to understand what is AI in games. Artificial intelligence in games refers to the technique and algorithms that allow non-player characters, that is called as NPCs, to act intelligently. So what is NPCs? Non-player character is a character in a video game that the player does not have the control over that character. Instead, the game's computer or otherwise the AI controls them. These characters are there to make the game world feel more alive and interactive. In this picture, if you play Mario, all other three characters are NPCs. When you play against a computer in chess, you control your own pieces like your bishop, your queen, making decision about your moves. But the computer or the AI controls the other side and moves against you. So here the AI acts like a non-player character, deciding its moves based on the chess strategies and rules. So now imagine giving video game characters a brain. That means they can think and act on their own. For instance, in a racing game, AI enables other cars to race against you, making the experience interactive and thrilling. The AI reacts to your actions, so it enhances the gameplay and keeping you engaged. It creates a dynamic environment where every decision matters. So now, before going into this, we need to understand what is adversarial games. Now, let us talk about adversarial games. These are the games where two or more players compete against each other with opposing goals. Adversarial games are the games where you play against someone else and you both want to win. You try to do the best you can while stopping the other person from winning. Think of chess or tic-tac-toe. Each player has a unique plan to win while trying to outsmart their opponent. In adversarial games, every move you make must consider what your opponent might do next. It is about maximizing your own success while minimizing opponents. This creates a challenging and enjoyable experience as you strategize against another player's decision. In AI, adversarial games involve creating intelligent agents that compete against one another. The AI needs to anticipate the opponent's move and make the best possible decision to win the game. When it comes to programming, there are several approaches that can be used to solve these problems. In that, the first approach involves the combination of analysis, strategy, and tactics. Analysis is about gathering information and understanding the current game situation. In chess, for example, analyzing the position of all the pieces helps to identify the threats and opportunities. Next, strategy means this guides your actions over time. It requires predicting possible outcomes and deciding on a long-term plan. Tactics or short-term moves or otherwise actions taken to achieve immediate goals. For example, in chess, you might set a trap for your opponent by sacrificing a piece. The challenge lies in effectively blending these three components because they all three operate on different levels. Analysis provides raw data, strategy offers a big picture, tactics involve a specific actions which may conflict with long-term goal. So the challenge is no single representation to capture all these aspects at once. The second approach is the if-then rules method. This is straightforward method involves programming behavior based on specific outcomes. For example, if the enemy is near, then attack. If you can move the queen to the next position, then move. So, in this method, this is very easy to implement, but it can handle only predefined situations. If the game state changes unexpectedly, then the AI may fail to respond appropriately. So, it may not be the best for games. The third approach is the more sophisticated approach. It is look ahead and evaluate. It allows the AI to anticipate future moves and assess their potential outcomes. Here, the AI generates the tree of possible moves starting from the current game state. For each possible move, it simulates how the game will progress and evaluate the likely consequences. This evaluation considers various factors such as positions of the player, available resource, strategic advantages. A scoring system is used to assess the desirability of the outcome. Normally, linear scoring polynomial can be applied to assign values based on different criteria, such as the value of a piece in a chess, or otherwise the potential threats, or otherwise opportunities. The main advantage of this approach is its focus on expanding all possible moves and their consequences to determine the best course of action. But the disadvantage is it does not consider how its current decision will impact future moves in the overall game strategy. If the AI only evaluates the next move without considering the future implications, it may overlook crucial strategies or traps set by the opponent. So, the fourth method approach is look ahead and evaluate as far as possible. This approach is the most advanced, allowing the AI to consider multiple moves ahead. This approach evaluates the potential outcomes across several levels before selecting the move that leads to the best overall result. One effective way of implementing this strategy is through MiniMax algorithm. This algorithm enables the AI to minimize its maximum potential loss, effectively balancing between offense and defense strategic manner. In the upcoming topic, the MiniMax algorithm will be explored. Following that, an enhanced, this is the optimization layered on the top of the MiniMax algorithm to make it efficient by reducing the number of nodes the algorithm needs to evaluate is known as alpha beta pruning algorithm. That also will be explored. So, before delving into these algorithms, it is essential to understand the basics of the game tree. Here, let us use chess as our example. Imagine you are playing a game of chess. At the beginning, all your pieces are on the board and you will have a chance to make your first move. This starting position is the top of the tree, which we call it as root. So, picture yourself as player 1 and ready to make a move from the position. Now, after your first move, let us say you decide to make the pawn forward. That creates a new point on the tree, just like a branch growing out from the trunk. From this new position, your opponent player 2 gets to make their own move. Just like that, there are many possible moves branching out from the starting position, and each move represents a new branch of the tree. As players continue to make moves, the game tree grows. It shows all different possible positions of the board. Each branch represents a different move that the player can take, and it continues to expand with every turn. At the end of the game, some branches will lead to winning positions. The others may lead to losing or otherwise draws. The end of the branches or the leaves of the tree represent the final results. The highest value indicates the winning possibility of the player 1, while the lowest value reflects the losing outcome. For example, 10 might represent the highest winning possibility for player 1, while -7 represents the worst losing outcome for player 1. This score will be calculated by considering many factors. For example, considering the material value, that means the player 1 has queen and 1 pawn. The player 2 has a rook and 3 pawns. We can assign the value to each piece. For queen, let us consider 9 points. For rook, 5 points. For pawn, 1 point. So, the score based on the material advantage might look like player 1 score is 1 queen, that is 9, plus 1 pawn is equal to 1, equal to 9 plus 1 is 10 points. The player 2 score will be 5 rooks, 5 for rook, that means 5 plus 1 for pawn is equal to 1, and then another 3 pawns are there, so that means 3. 5 plus 3 is equal to 8 points. You can consider other factors too, such as positional advantage, king safety, and many other considerations you can consider. By using the game tree, chess players can think ahead and plan their strategies. It allows them to visualize all the different ways the game can unfold, helping us to make smarter choices to outsmart their opponent. So in simple terms, let us say a game tree in a chess is like a big map of all possible moves and outcomes. It helps player see how the game can develop and guides them in making the best decisions. Now, let us explore how the MiniMax algorithm works. In the MiniMax algorithm, it is a decision-making algorithm widely used in game theory and AI for games like chess, checkers, tic-tac-toe. It helps to make decisions that lead to the optimal outcome when playing against an opponent. The goal of the MiniMax algorithm is very simple. Maximize your advantage while minimizing the opponent's. It assumes that both you and your opponent play optimally. If you are a maximizer, you try to get the highest score. If you are a minimizer, then you will try to minimize your score. The MiniMax algorithm works by evaluating the game tree to make decisions. Each leaf node represents the final outcome of the game. The heuristic algorithm assigns scores to the leaf nodes based on the factors. For example, in a chess game, the score will be calculated by considering the number of pieces available, the position of a king, the number of steps to reach the goal node, and etc. Whatever you want, you can consider. The win is scored positively, a loss negatively, and a draw is neutral. These scores guide the algorithm in choosing the best possible move. Here, let us try to explore how the MiniMax algorithm works. The score will be in the bottom of the leaf nodes. So, these are all leaf nodes. These are all the scores. These scores will be the scores in the perspective of the player at the top. This top layer is called as maximizer. So, the player at the top would like to dive a play as much as possible toward the big number. Here the big number may be 9. So, the maximizer will like to drive the play to the big number and tries to maximize the winning possibility. There is another player, his opponent, which we call as minimizer. he would like to get over to the minimum number, which is 1 in this example. Okay, so because his view is opposite of the maximizing player. The maximizer player wants to go to the maximum value, the minimizer wants to go to the minimum value. So he is trying to minimize the value of the maximum player. That is why here, since two players, maximizer, minimizer, so this is why it is called as MiniMax algorithm. So now let us learn how the players will make decisions by using the scores. The immediate near player to the leaf node is the maximizer player here. So here the player is maximizer. So the value from the perspective of maximizer player is, comparing to 2 and 7, which one has the maximum value? 7. So he never goes to 2 and this maximizer will goes to 7. So this node will get the value 7. Similarly, the maximizer will compare these two values, that means 1 and 8. So which one he will choose? He will choose 8 because it has the maximum value. So same way here 6 will be chosen and 9. Now we have to take the scores down at the bottom of the tree and then we back them up one level. The values are 7, 8, 6 and 9. Now the immediate near player is minimizing player. He can see 7 and 8 as the scores in the two nodes and he needs to minimize the value of the maximizer. So which one he will choose? 7 or 8? 7 is the minimum value. So he is going to the node 7. And then 6 versus 9, in that he is going to choose the value 6. Now the maximizer player can see 7 and 6, in that the maximum value is 7. So the maximizer will play 7. The maximizer will go from the root node to the left side of the node, and then the minimizer will choose the minimum value, so which is 7 here, and the maximizer will choose from 7 to another 7, but with some cutoff paths of the portions of a search tree. This will be done by the process called alpha beta. Here, if we can cut off some portions of a search tree, we don't need to check all the static values like MiniMax algorithms, which reduce the computational time. Now, let us consider the same problem that has been discussed in the MiniMax algorithm, and let us explore the alpha beta pruning. In the bottom, the maximizer has to play. Maximizer wants to go to the maximum value and the minimizer wants to go to the minimum value. So when the maximizer finds the value 2, it will understand that the maximizer knows that the value of the node cannot be lesser than 2. It knows that when it chooses to go down, if the next branch produces lesser value, then it has to select the value 2. So the maximizer knows already the score there will be equal to or greater than 2. Now with the next number, that is 7, which is greater than 2, it will take the maximum value, and now the maximizer will look for greater than or equal to 7. Now the minimizer sees this value and it will try to go for less than or equal to 7. In this, the next branch, when it sees 1, the maximizer selects 1, the minimizer will choose this path. So it will try to see another leaf value which is 8, which is greater than 7. So the minimizer will not choose this path. The minimizer will keep the value 7 as its best move. Now the top root node has to search for the static value which is greater than or equal to 7. When it sees the value here 6 and it already has the value 7, so it will not choose 6. Same applicable to 4 also. So the minimizer will choose the path which is less than 7. On the other nodes evaluation, it is not necessary because already the maximizer has the value 7, and if it chooses this path, then the value will come as 6. So for the given set of static values, some branches will be pruned without losing the accuracy. Now let us see one more example, but the same concept we have to use two values, alpha and beta. Because of that, this algorithm is known as alpha beta pruning algorithm. This is called alpha beta pruning because it passes two extra parameters in the MiniMax function, namely alpha and beta. Some of the conditions should be followed to understand this. So those conditions are, first one is, if the player is a maximizer, then modify the value of alpha. If the player is minimizer, you need to modify only beta value. So when you have to prune, if the value of alpha is greater than or equal to beta, then the remaining tree can be pruned. When you go down from the root, don't change any values of alpha and beta. When you go up from the leaf, change the value according to the player. If it is a maximizer player, you change only alpha. If it is minimizer, then you change only beta. And finally, the initial value of alpha should be minus infinitive and the beta should be infinitive. These are all the considerations that should be considered. Now let us solve the alpha beta pruning algorithm. In this scenario, the first player is maximizer and he is choosing the moves in the decision tree. The initial values of alpha and beta are alpha is equal to minus infinitive and beta is equal to infinitive. So now the maximizer begins at the top and passes these values to the minimizer. Same values. When you are traveling towards the leaf node, don't change any values. When the value reaches the next maximizer, the alpha value is equal to minus infinitive and beta value is equal to infinitive. Now, when it sees the first leaf node value to the higher value is 2 compared to alpha value, because this is a maximizer. So maximizer will compare only alpha value with the node. So which one has the maximum value? Minus infinity or otherwise 2? It is 2. So the alpha value will be changed to 2. After evaluating this node, now it will go to the next node, 7. Now it will check 7 compared to 2 and 7. 7 is the highest, so the maximizer will changes the alpha value to 7. Now there are no other leaf nodes, so the maximizer will process these values to minimizer. When it comes to minimizer, the minimizer will change only the beta values. So compare this beta value is infinitive, and then here which one has the minimum value, 7 or infinitive. 7 is the minimum value, so the beta value will be changed to 7. Now the minimizer will process these values to the next right side child. So same value will be passed. When it sees 1, alpha value is equal to minus infinitive, and then compared with 1, 1 is the highest value, so 1 will be changed. And now 1 with 8, when we compare, 8 has the highest value, so alpha value will be changed to 8. Now here the condition, pruning condition occurs. Alpha is greater than beta, so that means the tree has to be pruned. So this tree will be pruned and only these two values will be considered. And now when the minimizer passes these values to maximizer, then now minus infinitive and then 7, in that the maximum value is 7, so alpha value becomes 7. This one will be passed to the next node. Now alpha is equal to 7 and beta is equal to infinity. Same value will be passed here, and when it sees this one, 6, alpha value, we have 7 already, so 6 is lesser than 7, so no change will be done here. When we see 4, that time also no change will be done. So now when it changes, when it passes from here to this node, now beta value, this is the minimizer, so beta value will be chosen. So 7 and then infinitive, in that 7 is the minimum value, so beta value will be changed as 7. Here the pruning condition occurs. Alpha is greater than or equal to beta, so the next node will not be evaluated. So this entire node will be pruned. So by seeing this, you can understand the maximizer will choose the path which goes towards 7. So that means this maximizer will move its position from here to here. Now let us see one more example. We start with maximizer at the root node, and then the initial values are minus infinity and then infinity for beta. Same value will be passed here, same values will be passed, and then again same values. Now this is the minimizer, so beta value will be changed. Compare infinity with 8. 8 is the minimum value, so beta value will be changed to 8. Now compare with the next node 7. Beta value is 8 and the new value is 7. So the new value 7 is the minimum value. So beta value has been changed to 7. Now this value will be passed to the maximizer. When it changes, the maximizer will change only the alpha value. So alpha value has been changed with the maximum value among these two values, so that is 7. The same value will be passed to the next node. Alpha is equal to 7, beta is equal to infinity. When it sees 3, beta value is equal to 3. When it sees the next one 9, now beta value, now the alpha value becomes greater than or equal to beta value. So it will not evaluate the next subtree, it will prune the next subtree. So now this value will be passed to minimizer. In this, the minimum value is 7, so here beta value will become 7. The same value will be passed to the next node. Alpha is equal to minus infinity and beta is equal to 7, and vice versa. Now 7, beta value is 7. Now minimizer 9 value will not be chosen because already the beta value has 7, and then 8 also will not be chosen. So when now this value, new value will be passed, so here alpha value will become, compared to minus infinity and 7, 7 is the maximum value, so here alpha value becomes 7 and beta value already is 7. Now again the pruning condition occurs. Alpha is greater than or equal to beta. So it will not evaluate the next subtree. So it will go back and the values alpha is equal to minus infinity and beta is equal to 7. These values will be passed to the maximizer. In that, compared to this one, this is the maximizer. So alpha value has to be changed. In that, 7 is the highest value. So now alpha value becomes 7. The same value will be passed here, here, here. Now when it sees 1, the infinity and then 1 is the minimum value, so the beta value will become 1. And then compare to 1 and 8, 1 is the minimum value, and here the alpha value becomes greater than or equal to beta value. So the next node will not be evaluated, it will be pruned. So now here this is the maximizer. In that the maximum value is equal to 7, so the values will be kept as it is. So the same value will be passed to the next node, and beta value is equal to infinity with 8 when we compare 8, and then 8 and then 9, it is a minimizer, so 8 is the minimizing value, so 8. Now when it passes to this, the previous parent node. So now this is the maximizer. So 7 versus 8, the maximum value is 8, so it will be 8. This value will be passed to this node. Here this is the minimizer, so beta value will be changed. 8 and then infinity, which one has the lesser value? 8. So this value becomes 8 now. Now the same value will be passed to the next node and 9. Minimizer, so 8 will be taken. Again when it compares to 9, same 8 will be taken. Now these values will be passed. This is the maximizer. So the maximum value 7 and 8. In this 8 is the maximum value. So now here alpha value will be changed to 8. Alpha is equal to 8, beta is equal to 8. Now the pruning condition occurs. Alpha is greater than or equal to beta. So if it is same, then the next tree will not be evaluated and it will be pruned. So from this you can understand the play will go from the root node to this node, and then again left side node, and then right side node, and then left side node. This is how the alpha beta pruning works. So there are 2 additional problems for you to solve. This is the problem number 1 and this is the problem number 2. I hope this video gave you a better understanding of MiniMax algorithm and alpha beta pruning. If you found this information helpful, be sure to like and subscribe for more content like this. And if you have any questions or thoughts, feel free to leave them in the comment section. I would love to hear from you. Thanks for watching and I will see you in next video. Thank you.